Deep beneath our feet, nearly 6,400 kilometers below the surface, lies the heart of our planet, Earth's core. This superheated sphere of iron and nickel is not merely a static feature of planetary geology, it is an active dynamic engine that drives processes essential to life as we know it. Its immense heat, comparable to the surface of the sun, powers a global system that shields us, shapes our continents, and makes our world habitable. This internal furnace has been cooling gradually over billions of years, a slow and predictable process. But what if this cooling were to accelerate unexpectedly? What would happen if Earth's core cooled faster than all geological and physical models predict? The consequences of such a scenario extend far beyond the realm of theoretical geophysics. The heat radiating from the core is the primary driver of mantle convection, the slow churning of molten rock that moves tectonic plates. Without this engine, the very ground beneath us would change. Furthermore, the motion within the liquid outer core generates Earth's magnetic field, an invisible shield that deflects harmful solar radiation and cosmic rays. A rapidly cooling core would inevitably weaken this protective bubble, exposing the surface and everything on it to a barrage of high-energy particles. This is not a question of distant, abstract science, it is a question of global stability. The stability of our technological civilization is intrinsically linked to the stability of our planet's deep interior. Our global power grids, communication satellites, navigation systems are all vulnerable to the space weather that a weakened magnetic field would allow to reach us. For instance, a compromised magnetosphere would leave GPS satellites exposed, potentially disrupting everything from air travel to financial transactions that rely on precise timing signals. The question is not if the effects would be felt, but how quickly and how severely they would cascade through every system we depend upon daily, from the planetary to the personal. In this analysis, we will explore the real-world chain reaction that would unfold if Earth's core began to cool at an accelerated rate. We will begin by establishing a baseline, explaining the fundamental science of our planet's internal heat and the systems it powers. From the Riawan Kembriwe, we'll trace the initial consequences, examining the immediate effects on the geodynamo and tectonic activity. We will then broaden our scope to assess the system-wide impacts on our environment, economy, and society, before projecting the long-term outcomes over decades. This is a journey into a scientifically plausible, alternate reality to understand the silent engine that sustains our world. To comprehend the consequences of a cooling core, we must first understand the architecture of our planet's deep interior. Earth is composed of several distinct layers, each with unique properties. Crust. The outermost layer is the crust, the thin, brittle shell upon which we live, varying in thickness from about 5 to 70 kilometers. Mantle. Beneath the crust lies the mantle, a vast layer of silicate rock that extends roughly 2,900 kilometers deep. While predominantly solid, the mantle behaves like an extremely viscous fluid over geological timescales, slowly churning in response to heat from below. Deeper still, we arrive at the core, which is divided into two parts. Outer core. The outer core is a 2,200 kilometer thick layer of liquid iron and nickel, with temperatures reaching between 4,000 and 5,000 degrees Celsius. It is within this turbulent metallic ocean that the planet's magnetic field is generated. Inner core. At the very center of the Earth is the inner core, a solid sphere of iron and nickel about 1,220 kilometers in radius. Despite being even hotter than the outer core, reaching temperatures over 5,200 degrees Celsius, comparable to the surface of the sun, the immense pressure at this depth forces the metal into a solid state. The boundary between the solid inner core and the liquid outer core is a zone of profound importance. Here, the slow crystallization of iron from the liquid outer core onto the solid inner core releases both heat and lighter elements. This process drives convection within the outer core. Much like cooling water at the surface of a pot, sinks and drives circulation. The transition between the mantle and the outer core, known as the core-mantle boundary, is another critical interface. It is a complex region where the hot liquid metal of the core interacts with the silicate rock of the mantle, influencing heat exchange and the behavior of both layers in a dynamic feedback loop. The crust is where we live, but its behavior, from earthquakes to volcanoes, is dictated by the motion of the mantle. The mantle, in turn, is moved by the immense heat escaping from the core, and the core itself, with its distinct liquid and solid components, acts as the planetary engine that generates our magnetic shield and governs the thermal evolution of Earth. Any significant change in one layer, especially a rapid change in the core's temperature, will inevitably cascade through the others, with direct and tangible effects on the surface. The immense heat within Earth's core is not a static remnant of the past, but is sustained by active processes that function as a planetary-scale engine. Primary source: primordial heat, a legacy of violent formation about 4.5 billion years ago. Gravitational collapse of dust and gas and constant bombardment by planetesimals generated enormous thermal energy, much of it trapped inside the planet. That ancient heat has been slowly radiating outwards ever since. Second source: continuous radioactive decay, uranium-238, thorium-232, potassium-40. These elements in the crust and mantle undergo decay over billions of years, releasing heat. Third source: latent heat of crystallization, released at the inner-outer core boundary. As Earth cools, molten outer core iron crystallizes onto the inner core, causing it to grow by about 1 millimeter per year. This latent heat feeds outer core convection, stirs liquid metal, and powers the geodynamo. Together, primordial heat, radioactive decay, and latent heat determine total interior-to-surface heat flow. Estimated flow: about 47 terawatts, equivalent to the energy of thousands of power plants operating continuously. The balance between heat generation and heat loss is delicate and formed over geological time. A sudden acceleration in cooling would disrupt that balance, fundamentally altering the energy budget that powers our living planet. If Earth's core began to cool at an accelerated rate, the first and most critical consequence would be in the planet's magnetic field. The geodynamo relies on vigorous convection in the liquid outer core and is exquisitely sensitive to thermal change. Faster heat loss would reduce the temperature difference, slowing the churning motion of molten iron. Slower convection means weaker electrical currents and a diminished magnetic field. This wouldn't be instant, rather a progressive decay, a faltering shield that has protected Earth for eons. Detectable changes would appear within months to years. Our global magnetometer network would register a troubling trend, a steady decline in geomagnetic strength. The magnetic poles, already wandering, would move more erratically and faster. One early effect: the South Atlantic anomaly would expand and intensify, a known weak spot where satellites are vulnerable to radiation. That region would preview a world with a weaker magnetic shield. As the field weakens, auroras normally at the poles would start appearing at much lower latitudes. Spectacular to see, but an ominous sign of increased high-energy particle interaction. Astronauts on the ISS would face much higher radiation doses, forcing stricter safety protocols, limiting EVAs, and, possibly, evacuating during severe solar storms. The weakening won't be uniform or predictable. The magnetic field is complex, and a loss of dipole strength could produce a multipolar, chaotic field. Critically, the shield becomes weaker overall, and riddled with temporary holes and thinner spots. That sets the stage for a cascade of technological and environmental consequences, beginning with our assets in orbit. While the most immediate effects of a cooling core would be felt in the magnetosphere, the planet's geology would also begin to respond, albeit on a slightly longer timescale. A rapid reduction in heat output from the core mantle boundary would act like a brake on the system. The first observable geological signs would likely be related to hotspots, surface expressions of deep mantle plumes. Volcanic island chains like Hawaii would experience a gradual but measurable decline in volcanic activity. Seismologists and volcanologists would detect changes in magma flow and a reduction in the deep harmonic tremors often associated with active plume systems. Changes in broader plate tectonic movements would be far slower to manifest. However, the forces driving the plates would begin to change. A slowdown in convection would reduce the ridge push force, potentially slowing the rate of seafloor spreading. Initially, these shifts would be detectable only by the most sensitive instruments, like the global network of GPS stations that measure plate motion down to the millimeter. Over a period of several years, these tiny changes could begin to alter the patterns of stress accumulation along major fault lines. It is plausible that this redistribution of stress could lead to a temporary and localized increase or decrease in seismic activity as the tectonic system adjusts to its new energy budget. The initial consequences of a cooling core would trigger an immediate and urgent response from scientific and governmental bodies responsible for monitoring global systems. These converging data streams would move the scenario from theoretical possibility to active crisis. In response, governments and private satellite operators would be forced into a defensive posture. This could involve putting satellites into a protective safe mode during predicted solar storms, leading to more frequent service disruptions. On the ground, the focus would shift to protecting the electrical power grid. A weaker magnetic field makes the grid far more vulnerable to geomagnetically induced currents, which can overwhelm transformers and cause widespread blackouts. Power utility companies would have to revise their operating procedures. They would need to lower operating thresholds and be prepared to disconnect parts of the grid preemptively based on space weather forecasts. This new planetary condition would spur a massive reallocation of scientific resources. International collaboration would become paramount as nations pool their data and expertise to build a comprehensive, real-time picture of the evolving threat. As the initial geophysical changes stabilize into a new normal, the system-wide environmental impacts of a weakened magnetic field would become increasingly apparent. The most direct consequence would be a significant increase in radiation reaching the Earth's surface and atmosphere. This would have profound effects on atmospheric chemistry. For instance, these high-energy particles would create nitrogen oxides, NOx. These compounds are highly effective at catalytically destroying ozone. This would lead to a measurable depletion of the ozone layer, exposing all life on the surface to higher levels of harmful ultraviolet, UVB, radiation from the sun. Phytoplankton in the upper layers of the ocean, which form the base of most marine food webs, are particularly vulnerable to UV radiation. A decline in their populations could trigger a catastrophic cascade effect. On land, agricultural systems would also be stressed. Many staple crops, like rice, are sensitive to high levels of UV radiation, potentially leading to reduced yields and threatening global food security. Furthermore, the planet's climate systems could be subtly influenced. Some scientific hypotheses suggest a link between galactic cosmic ray influx and cloud formation. A significant increase in cloudiness could alter the Earth's albedo, reflecting more sunlight back into space, and possibly inducing a slight cooling effect on the global climate. Finally, the biosphere would have to contend with the direct biological effects of increased radiation exposure. The cumulative, long-term increase in background radiation would raise the mutation rate in all organisms, primarily manifesting as an increased incidence of cancers and genetic defects in more complex animals and humans. The new reality of a weakened magnetosphere would send a powerful and sustained shockwave through the global economy, beginning with the multi-trillion-dollar space industry. The operational lifespan of satellites would be drastically reduced. On the ground, the airline industry would face a severe reckoning. Radiation at cruising altitudes would exceed safety limits. Airlines would cancel or reroute hundreds of flights daily. Detours mean longer flight times, much higher fuel use, and higher operational costs. National power grids become permanently vulnerable. Utilities must overhaul infrastructure, installing GIC blockers and upgrading transformers. The upgrade cost runs into the trillions, passed on to consumers and taxpayers. Ripple effects hit other sectors. Precision agriculture, reliant on automated tractors and targeted fertilization, would suffer from reduced GPS accuracy. Supply chains optimized for just-in-time delivery would be disrupted. The economy would recalibrate from pure efficiency towards resilience and redundancy. The magnetosphere's invisible shield now carries a steep price tag, forcing a costly reevaluation of risk across the global economy. The pervasive and disruptive nature of a weakening magnetic field would create profound societal and political challenges. In the realm of public health, governments would face a difficult balancing act. The increased surface UV radiation would lead to rising rates of skin cancer and cataracts. Economically, the crisis would exacerbate inequalities. Nations with advanced space programs would be better positioned to adapt, while developing nations would be left further behind. This magnetogap could become a major source of international friction. Governance would be strained, the necessary regulations would be met with public resistance and economic opposition. Misinformation and conspiracy theories would likely proliferate, undermining public trust. This new shared vulnerability could, however, also serve as a powerful catalyst for international cooperation. The clear and present danger of a failing magnetosphere would necessitate an unprecedented level of scientific and political collaboration. Over the span of decades to centuries, the persistent cooling of the core would usher in a new geological epoch. The magnetic field, having weakened significantly, would likely settle into a new, much lower energy state. The engine of plate tectonics, driven by mantle convection, would noticeably slow over longer timescales. With less heat from the core, the mantle's churning becomes sluggish. Plate movement would gradually decrease. Consequently, major geological events would become less frequent. New mountain formation would slow. Volcanic activity, especially from deep mantle hotspots, would wane significantly. This slowdown has profound implications for the carbon cycle. Less volcanism means less CO2 released from the interior. Over thousands of years, that contributes to gradual global cooling. Earth would transition toward a colder, less geologically dynamic state. It would start to resemble Mars, whose core cooled billions of years ago, causing loss of its magnetic field and tectonic shutdown. Over millions of years, mountains would wear down. Topography would become subdued and flattened. The planet would enter geological old age prematurely. The Earth would remain living, but its planetary pulse would have weakened, setting it on a path to a less energetic future. Faced with a permanent environmental shift, human civilization would be forced to make fundamental adaptations to survive and thrive. The decades following the initial crisis would be defined by a massive global engineering project to build a more resilient society. A new generation of satellites would be designed with heavy radiation, shielding, and redundant systems, managed by international consortiums. On Earth, the power grid would be fully decentralized, with localized renewable sources and hardened microgrids less susceptible to geomagnetic storms. Societal norms and behaviors would shift. Space weather becomes an everyday forecast, influencing decisions from aviation and power management to personal travel and outdoor activities. The stark reminder of our planetary fragility would provide an impetus for humanity to become a multi-planetary species, establishing self-sustaining outposts on the Moon and Mars as a critical long-term survival strategy. Ultimately, the long-term outcome for humanity would be a civilization forged in the crucible of adaptation. While the Earth would become more hazardous, humanity would become more technologically robust, more scientifically aware, and potentially more unified. Our journey reveals a profound truth. Habitability isn't just a surface phenomenon, it depends on the immense silent engine of heat in the planet's core. An accelerated core cooling shows two critical mechanisms: the geodynamo, which provides our magnetic shield, and Mantle, convection, which drives the renewal of the ground beneath our feet. To imagine their faltering is to see the fragile equilibrium that let our technological civilization flourish. Our most advanced technologies, satellites, power grids, global communication networks, are sensitive to this. This thought experiment teaches resilience over mere efficiency. The impacts across society, politics, and the global economy demand international cooperation and science-informed governance. The core's temperature is the planetary baseline for our global system. Science and policy would guide us through such a crisis. The immediate priority: expand monitoring capabilities to build a comprehensive, real-time dashboard from the deep core to the upper atmosphere. Though hypothetical, the scenario is a lesson in planetary stewardship. It reminds us we're inhabitants of a living planet, sustained by the echo of its formation. You've been watching Ifverse, where imagination meets possibility. See you in the next reality. What scenario should we explore next? Share your ideas below.